Now we're going to take a look at the standard form of a quadratic function and how you can find different parts of a parabola, which is the graph of a quadratic function, okay, based upon the standard form. The first couple things that you can find from the quadratic function are the x and y intercepts. I think those may be the easiest things to find. So to find the y-intercept, very simply, you always replace the x with 0, right? So you have f of 0, which is then equal to a times 0 squared plus b times 0 plus c. Well, obviously the first two terms, anything with an x in it, originally becomes 0, and all you're left with is the c. So 0 comma c will be the y-intercept. And in fact, that constant will always be the y-intercept on a quadratic function, okay? In the same way that the constant on a linear function is the y-intercept, right? The y equals mx plus b. The constant there on the end is your y-intercept, because when you plug in the 0, the mx part or mx term drops out. Okay, so same idea. The constant is your y-intercept. Okay, now the x-intercept is interesting. If you consider this, the x-intercept is where you put the 0 in for the function value, right, for the y. So 0 is equal to ax squared plus bx plus c. Well, we know that to solve this, what we call a quadratic equation, requires a quadratic formula, okay? Well, actually, there's multiple different processes. You could factor this potentially, or you could use completing a square. But as a general principle, the quadratic formula will work for all quadratic equations in this form. So we have potentially two x-intercepts, right? One using negative b plus, one using negative b minus the square root of b squared minus 4ac all over 2a, right? So the quadratic formula is what solves a quadratic equation, and there are two answers, one with a plus and one with a minus. So that would imply that we would have two x-intercepts. But remember, parabolas don't have to have two x-intercepts. They could have the case where there's two x-intercepts, that's a potential, right? But you could also have a case where there's one x-intercept right at the vertex, or where there's none at all, where the graph never gets down that far. Or if you flip all these upside down, you could make it work for them opening downward as well. Same three situations, 0, 1, or 2 x-intercepts. With the quadratic formula, the way that that works out is that if the stuff under the root here is negative, right, then you end up taking the square root of a negative number. That gives you no x-intercepts, because those are complex numbers. They don't show up on the real number line. So if, I'll just write this off to the side, if that stuff under the root, we call that the discriminant, there's actually a name for it. If that discriminant is negative, then there are no x-intercepts. Okay, and the reason again for that is because when you take the square root of a negative, you get a complex number which cannot be plotted on the number line, so you don't actually hit the axis there. However, if that discriminant is positive, greater than 0, then there are two x-intercepts. Right, you're going to have whatever you take the square root of the positive number, you get the plus or the minus of that, and that gives you your two values. Now there is a third option, and that is if the discriminant is equal to 0, right? If b squared minus 4ac equals 0. Well, in that situation, the square root of 0 is 0, and so when you add 0 and subtract 0, you get the same answer. So you really get one x-intercept. Okay, I realize my grammar is poor here. I'm just jotting some notes quickly. Okay, so those are three situations you can have, three graphical situations with the x-intercepts and how they occur algebraically. Okay. Now, what's interesting is that if you had two x-intercepts, then the vertex would be halfway in between them, right? In fact, the axis of symmetry, which goes through the vertex, cuts the graph in half, must be exactly halfway between two symmetric points, including the x-intercepts. And so, in order to find a number that's halfway in between, so I can find that vertical asymptote, axis of symmetry, so I can find that axis of symmetry, I could average the two x-intercepts, right? I could add them together, divide by 2, that gives me the number directly in the middle. And that's how we can find the vertex and the axis of symmetry both. So let's take a look at what happens when we take that average or calculate that average. I'll do this very quickly, maybe not showing all of the details. To find the average of the two x-intercepts, which is the middle point, you have to take the two results from this formula, add them together, and divide by 2. So think about one of the x-intercepts being what you get when you add in the formula, and the other x-intercept is what you get when you subtract. Right, so those are your two answers, or your two x-intercepts separated out from the formula. Well, if I average them, so that would be your asymptote again. Let me maybe sketch this off to the side here. Not asymptote, I keep saying asymptote, I don't know why. We're going to talk about asymptotes in chapter 5, I believe, but right now they're not here. So the axis of symmetry is what I want to refer to here. The axis of symmetry, again, is halfway in between. So, and remember, the axis of symmetry is your h value from the vertex form that we talked about before. And so that h value must be the average of the two x-intercepts. So you add them together and divide by 2. That's how we take the average. If I take the average of those, if I add those together, I'm adding these two big fractions together, which sounds horrible. But what's nice about it is that the positive root over 2a and the negative root over 2a will end up canceling each other out when you add them together. Right, so this portion and this portion end up dropping out. I won't go, like I said, I'm not going to show all the details here, but that's what happens. When I add them together, when those roots drop out, is I'm just going to have the negative b over 2a plus another negative b over 2a, all divided by 2, right? The two x-intercepts kind of reduce down to these two expressions when the roots add out to 0, okay? So I've done a little work already here in the ... Then, if I'm adding two of the same thing together, I could just multiply by 2. I'd have 2 of the negative b over 2a all over 2. And then the 2's cancel. And I'm just left with negative b over 2a. That's actually going to be our formula for the axis of symmetry. Negative b over 2a, right? It's essentially, or it's exactly, the first term here in the quadratic formula. Okay, so that gives us a nice, neat formula for finding the axis of symmetry, and also gives us a way to find the vertex. Right, so for any quadratic function, the axis of symmetry is going to be x equals negative b over 2a. Okay, it's that same value. The vertex is going to be negative b over 2a. That's your x coordinate, right? That's what lands on the axis of symmetry. But then you also need a y coordinate. Now, how do I get a y coordinate? Well, once I find the x, I just plug that back into the original function to get the output. So we would say that that is f of negative b over 2a. And so there's your x and y coordinates of the vertex. Now, it's not as simple as just h and k from the like we had in the the vertex form, but the formulas still work out. Now, this does simplify to another formula that I could put up here, but it's kind of a lengthy formula and I don't really care that you know it. This is good enough. So just find negative b over 2a, plug it back in, you get your other value. Okay, so that gets us pretty much everything we need in order to plot the graph of a quadratic function in standard form. A couple other things though to keep in mind. The value on the a does determine whether the graph opens up or down. So if the a is positive, if a is greater than 0, the graph opens up, and if a is negative, the graph opens down. Your book may call it faces up, faces down, but same idea. Okay, so opening up, that one, opening down, points down on the ends. Okay? All right. Now, one thing I want to mention also is the domain and the range. The domain on a quadratic function is always all real numbers. Okay, that never changes because you can plug anything into this. These operations are not limited. So the domain is going to be all real numbers every time. Okay, no matter what. Now the range depends. The range depends upon two things: the a value and the vertex. Okay? If you have a situation where the graph opens up, then you have a minimum at the vertex, and the range goes from that point up to infinity. Okay? So, let's look at, maybe I'll need to erase a couple things here, make a little space. Alright, so let's say that a value is positive again, which implies that the parabola opens up. Then the range is going to start at the y value of the vertex, f of negative b over 2a, and it's going to go up to infinity. Okay, so that would be your range on a parabola that opens up. Now, if we were looking at this in the vertex form, it would just be k comma infinity. If the a value is negative, the parabola opens down, then it starts at negative infinity and comes up to that function value, that maximum. So then the range would be negative infinity up to f of negative b over 2a. Right? So the order changes because you're going down to negative infinity rather than up to infinity. Okay? Okay. We'll go through in the next example, or in the next video, we'll go through some examples of finding this information and then plotting the graphs.